All right, this video is how to determine and explain the polarity of a molecule using geometry and bond polarity. So we're talking about the polarity of a molecule. We already talked about the polarity of a bond, and we're going to use similar terminology. So we're either going to talk about a polar molecule or a non-polar molecule. The reason that we're going to do this is because this distinction starts to explain why some molecules have very high boiling points, why some have very low boiling points, why some will mix. So, oil and water will not mix. That is going to be because of the polarity of the molecules. And so we can start making predictions as to how different substances will interact with each other, as well as when they will start to boil away. So let's get started. All right, so to know whether a molecule is polar or not, you're looking for a separation of charge where you have one end that is positive, and you're going to see a delta plus on that end, and another end is negative. Or we actually could have something that's positive and another part is neutral, but there's going to be a difference. It will not all be the same on the outside. When we have that, we say the molecule is polar, or it has poles. It has one positive end, one negative end, or one end that's more positive, one end that's more negative. So to look at this, we need to look at three things: the lone pairs on the center atom, the VSEPR shape, those are going to become very important, and the bond polarity and dipole arrows. So first off, I like to refer to this as polar reason number one. So we're going to give you molecules and ask you, is the molecule polar or nonpolar, and then ask you to explain. So polar reason number one is that there are lone pairs on the center atom, and that will create a large negative charge on that area, causing the molecule to be polar. All right, so that's one of the easiest things for you to evaluate about a molecule. You'll notice that we say that they're not cancel it out. In everything we do in first year chem, they will not be able to be canceled out, but anyone moving on to beyond that, recognize that in second year chem, you'll see molecules where that can happen. But right now, you don't need to worry about that. All right, second thing is the VSEPR shape. All right, so right away, bent and trigonal pyramidal. Both of these are polar molecules. So as soon as you identify it as bent or trigonal pyramidal, it is going to be a polar molecule. And I want you to think about what's similar about both of those VSEPR structures. And what they have in common is they both have lone pairs. So that's why we know. So it's going to be a polar molecule. And the reason is C, reason number one, that the lone pair produces a large negative charge in one area that can't be balanced out. All right, then we have, if we're looking at the other ones, linear, trigonal planar, tetrahedral. All right, it's not as straightforward. Those can be either polar or nonpolar. If they do not have a lone pair, then they will be nonpolar if all the elements around the center are the same. All right, so that is something you're going to keep in mind, and we'll see that in a couple of different examples. All right, if we are looking at the linear, the trigonal planar, or the trigonal pyramidal, now we have to look at the dipole arrows. So I'm going to go to the second bullet point first. So this is what I call polar reason number two. Once it's polar, there's only only two possible reasons you could give us or explanations for it being polar. Polar reason number two is that the dipole arrows do not cancel each other out. All right, so we'll show you examples of that as we go. Then we have our first non-polar reason. This is the main one you're going to see. There is another one, but we won't. So we'll see that when we start talking about intermolecular forces. But for the purpose of this learning target, your non-polar reason number one is going to be that if there are dipole arrows in the molecule, they will cancel each other out. All right, so that means that everything is going to be the same around the outside when the dipole arrows cancel each other out. And again, I'll show you examples of what that means. Okay. All right, let's look at these two molecules. All right, a lot of similarities here. We've got carbon monoxide and carbon dioxide. They both have polar bonds. The carbon-oxygen bond is a polar bond, so we've put the dipole arrows in, and I'm also going to add the delta symbols, because sometimes I find that looking at the delta symbols makes it a little bit easier to identify the positives and the negatives. All right, and then the VSEPR structures are similar as well. So this is where we really need to decide, are the dipole arrows canceling each other out or not? So in this structure on the left, the dipole arrow is not canceled out. There's only one of them, so it can't be canceled out. In this one, dipole arrows are canceled. You can see that they're going in equal and opposite directions. Or dipole arrows canceled. Sorry about that. All right, so they have, if you think about, focus on that center atom, in this structure on the right, there's the same pull in this direction and in that direction, and there's no pull in any other direction. So you can think about, okay, well, it's being pulled equal, so I have just two negative ends. There's no positive on the outside. So that is going to be a non-polar molecule. So that is dipole arrows canceling out. And then the one on the left is going to be a polar molecule because there's nothing to cancel that arrow out. I have a separation of charge in that molecule. I have a negative on one end of the molecule and a positive on the other. All right, let's start getting to other examples. All right, start with H2O, which from biology days, probably already know that this is going to be a polar molecule, but now we want you to be able to explain why. So using the dipole arrows and the lone pairs. So figuring out the electrons first. So I've got one electron from each hydrogen, but there are two hydrogens. And then I have 6 coming from the oxygen. So I have a total of 8 electrons. Oxygen in the center, hydrogen, hydrogen, lone pair, top and bottom. All right, so bond polarity, first thing I have to look at is what's the bond polarity. So looking at my electronegativities, which again is the only way you know what the polarity is, hydrogen is 2.1, oxygen is 3.5, for a difference of 1.4, making this a polar covalent bond. All right, then I'm going to do the VSEPR geometry right away. Okay, so I look at this and I have 2 atoms around the center. Yes, there are lone pairs, which means that this is a bent structure. All right, so when it's a bent structure, sometimes, actually not sometimes, but all the time, when students put the dipole arrows in to a bent structure in the Lewis dot structure, which I'm going to do right away, it's a little misleading. So if I put these dipole arrows in, it sure looks like what I had earlier. All right, earlier I had this, and I had dipole arrows. Sorry, take me a second to get to my eraser so I don't accidentally erase everything. Oh, there we go. Okay, faster than I thought. So we've got dipole arrows going in. Oh my gosh, that's totally the wrong structure. Let's back that up. Get my eraser back. Sorry about that. I want CO2, so I need the carbon in the center. This happens sometimes. Oops. All right, C, double bonded to O's, and then the O's have some lone pairs on them. All right, then I put my dipole arrows into that one from the carbons to the oxygens. Okay, so again, we have, even though the dipole arrows are going opposite directions, in a linear structure, they're going to cancel each other out. So you might look at that bent structure and be like, oh, wait, they're going equal and opposite. But here's the thing that you have to remember about the bent structure. The bent structure, and I'm going to redraw it, and you don't need to do this, but you're welcome to do it as you're trying to figure this out. That bent structure, now if I draw it in the correct geometry, now the arrows, because they're at angles, they do not cancel each other out anymore. And so that's what you need to remember about your bent structures, is that the Lewis dot structure can be really misleading. And so drawing it in the bent arrangement makes it a little bit more sense. Or you can just remember that, oh, it's bent, then it needs to be polar, and then you need to get your reasoning. So this is a polar molecule. All right, and I actually could use, we had 2 different reasonings why it was polar. I could actually use either of them in this case. Both of them would work. So I could say because there is a lone pair on the center. Oops. I'm just going to, it's faster than using an eraser. Creating a large negative charge. And again, we do want you to add that second part, creating a large negative charge. All right, so that would be sufficient enough. Or in this case, and you can't always do this, but in this one, you could give the you could give the reason that the dipole arrows do not cancel each other out. All right, so either of those would work, but you definitely need to have one of them. All right, let's move on to the next example. All right, CF4. So carbon in the middle, I have 4 fluorines. All right, I just sped up that process by adding my lone pairs. So that is my low structure. Next, I need to think about the bond polarity, what I have. So carbon and fluorine are my 2 bonds. So carbon is 2.5, fluorine 4.0. So difference is 1.5, making this a polar covalent bond, which means I will need to put dipole arrows in, but I'm going to do the Vesper geometry first. We have 4 things around the outside, which means it is tetrahedral. Again, tetra, if you think back to when we were doing covalent naming, tetra was 4. So it's nice, it stays consistent. So I'm going to add my bond polarity in to evaluate that, because again, since it's tetrahedral, I need that in order to know if it's polar. So since fluorine has the higher electronegativity, those all go out toward fluorine. And I'm going to add the delta symbols in. I should have actually done that on the water one too. So I've got delta minus, delta minus, delta minus, delta minus, delta plus. Okay, so this is where I think the delta symbols do a really good job of helping you understand whether the outside is all the same. Because remember, in a polar molecule, the outside, you're going to have a difference in charge. So one area is going to be more negative than the other. So if I look around this entire outside, it is all I see is negative charge. Because remember, it's a 3-dimensional thing. So this is actually a non-polar molecule because it's all the same on the outside. So non-polar. But then you want to think back to the reasoning. Now look at your dipole arrows. The dipole arrows are equal and opposite all around the carbon. There's nothing different. So it is a nonpolar molecule because the dipole arrows cancel each other out. All right. Okay, let's do another tetrahedral structure on the next one. All right, so with this one, you notice the only thing we changed is instead of 4 fluorines, there's a hydrogen and 3 fluorines. So I'm going to get my low structure up here pretty quickly. All right, so magic of video making. So I have my structure. I have 2 different bonds, and so I have to evaluate their polarities differently. So I have 1 polar covalent bond and 1 non-polar covalent bond. And again, 4 atoms around the center, so it is a tetrahedral molecule. So I'm going to put the dipole arrows in and my delta symbols to get a better vision on whether these dipole arrows cancel out. Because if it's tetrahedral, there's no lone pairs. So I need to think about, okay, what's going on with the dipole arrows and the charges, and do I have a difference or a separation in charge on the outside of the molecule? And in this case, you'll notice I have 3 delta minuses, and then I don't have anything on that 4th spot. So I do have, in this case, a polar molecule because I have a difference in charge. It's not all the same on the outside. So remember, with these tetrahedrals, if it was either all fluorines on the outside, or, so a CF4, we saw it was nonpolar. CH4 would also be nonpolar. Then, because they're all the same, they're all nonpolar. But as soon as I change something, then I know that it's going to be polar because I don't have the same thing on the outside. So polar molecule, thinking about my two reasonings, the lone pairs doesn't work because again, the lone pairs have to be on the center atom because that's what we're evaluating is the charge difference around that center atom. So this is a polar molecule because the dipole arrows do not cancel out. So I have poles, I have a dipole, one end, I have kind of the bottom end, if you think about it as a three-dimensional structure. The bottom end is negative, the top is relatively positive. All right, we've got one more example. All right, PI3. So again, I'm going to get my stuff going. So if you want to stop the video, get your Lewis structure, bond polarity, VSEPR geometry, go for it. All right, there we go. So I've got my Lewis structure. Again, it's really important that you figure out your number of valence electrons. So in this case, the P is there's 5 coming in from the phosphorus. Each iodine has 7, but there are 3 iodines for a total of 26 electrons. If it was 24 electrons, there would have to be a lone pair somewhere, changing it to trigonal planar, changing the polarity. So that lone pair of electrons is going to make a big difference because it's sitting here all negative, which is different than the other sides of the phosphorus. So this one is a polar molecule. All right, and then again, there's no dipole arrows. So the only thing, but I do have a lone pair. So my reasoning, polar molecule, because there's a lone pair on the center, which creates a large negative charge. All right, and that is molecule polarity. Hope it helps.